So our third speaker in this session is Alekseyev, who's coming from George Washington University. He's doing work both in mathematics and in philosophy. So, but tonight, in philosophy, in biology. But today it's going to be mostly math, right?
Yes.
Good.
It's a great pleasure for me to be here, and thank you, the organizers, for giving me the opportunity to present some of my computational experiments. And I will talk about two types of equations today. One is pure exponential equations, and another one what I call exponential-polynomial Diophantine equation. Let me start with the first one. So under exponential Diophantine equation, I understand the equation of the form c1 times b1 to the power n1 plus c2 times b2 to the power n2, and so on and so forth. There, the bases b1, b2, and so on are positive integers, and c1 and so on, ck are just integers, maybe positive, maybe negative. And this equation needs to be solved in non-negative integers n1, n2, and so on, and k. So here's a particular example. Equation of the form 2 to the power n minus 3 to the power m equals 7. So how to solve this equation? Okay, let me show you some street magic.
4 and 2.
Let us compute powers of 2 modular 2720. Here we are. We start 1, 2, 4, 8, 16, 32, and so on. 1376, and then 32 again, 64, 128. So what I have in brackets here is the period of the sequence modular 2720. And let me compute powers of 3 modular the same modular. And here the period starts from the very beginning, and the period is rather long, but still all the period is shown on this slide. Now let P2 be the period of powers of 2, and P3 be the period of, as I said, of powers of 3. And it can be easily verified that the difference x minus y is never 7 if x is from P2 and y is from P3. So what it means? It means immediately that n must be at most 4. So in the solution, only those powers that are not in the period may give us a solution to the original equation. And therefore, we can just iterate for n over 0, 1, 2, 3, and 4, and compute the corresponding m if it exists. And this way, we get just two solutions, 3, 0, and 4, 2. So I expect that you say, wow. Want more magic? I have some. Consider equation 7 to the power n minus 3 to the power m equal 4. This time, let us consider its modulo 234. So here powers of 7, powers of 3. It can be easily verified that x minus y is not 4 modulo 234 if x is in the period for powers of 7, y is in the period for powers of 3. Therefore, we immediately conclude that m must be at most 1. So should come from non-periodic part of the corresponding sequence. And this immediately gives us that there is only one solution, 1, 1. Okay, 2 more equations. Equation 2 to the power n minus 5 to the power m equal 3. This one can be solved modular, what is it? 3,355,392. The magical modulus. And similar equation 2 to the power minus 3 to the power m equal 5 can be solved modulo 5,440. And we get all the solutions for both of these equations. Okay, more equations. Let us consider equation 2 to the power n plus 3 to the power n equal 5 to the power k. Now I have more non-trivial powers. Namely, before I considered just 2 non-trivial powers, now I have 3. Okay, let us take modulus 1632. Here are powers of 2, here are powers of 3, here are powers of 5. And again, it can be verified that x plus y never equal to z if x from P2, y from P3, and z from P5. Therefore, we have either n is less or equal than 4, or m is equal to 0. So at least one of x, y, and z must come from non-periodic parts of the corresponding powers. This reduces the original equation to 6 of the following equations. Right? The equations that were similar that you considered before. And each of them can be solved with the aid of some modules. Similarly how I did before. Okay, even more complicated, even equation not of the form which I presented before. Here I have 2 to the power a times 3 to the power b minus 5 to the power c times 7 to the power d equal to 1. Okay? Here's 48 works. Here powers of 2, powers of 3, powers of 5, powers of 7. It can be verified that if we take numbers from the periods, we can never get equality. Therefore, at least one of the numbers must come from non-periodic part. It means that we either have a is at most 3 or b equals 0. Therefore, we have reduction to one of the following 5 equations. And we can, again, apply similar approach. Okay, how to find the modulus? Short answer, I do not know. And here's the long version. I have some guidelines how to search for suitable modulus. Namely, the first guideline is that the periods of powers of each of the bases, modulo m, must be rather short. So the shorter they are, the more likely we got situation that there are no solutions that come from the periodic parts. And second guideline is that suppose we choose some modulus, and it happens that for this modulus we have some periodic solution. Well, then we can eliminate this periodic solution by simply introducing a large power of one of the bases to the modulus. For example, if our solution is a periodic solution is P1, so on Pk, values of N1 and so on and K, then if we introduce either of Bi to the power Pi plus 1 to the modulus, this periodic solution will disappear. It would not be periodic anymore. Okay, I implemented these guidelines in iterative procedure, which works well for many of the equations, and the results which I presented before, it was the moduli were generated by this procedure. And here's how it roughly works. I will address the case just for the most simple case when all the bases are pairwise coprime. And then the procedure constructs the suitable modulus m iteratively, and it starts with modulus 1. It's clear that 1 wouldn't work, but still it's just a starting point. And suppose that there is that for the current m there is a periodic solution. Then we need the procedure does is construct a set of new candidate moduli, and it does the following. Initially, we let our set be empty set, and then we go through all the bases. So j is the index of the base. It goes from 1 to k. Then we check what is the current power of bi in the m. So this is what is called bi-adic valuation of m. So the largest power of bi which divides m. And I let d be one larger than this power. So basically I'm going to increase the presence of bi in my modulus. Then for each I from 1 to k except j, I let the I be in multiplicative order of bi modulo bij to the power d. In other words, I find small such number that bij to the power d divides b to the power zi minus 1. And then I let integers v1 so on v sub k run in certain small intervals, say from 1 to 20, all various combinations of these numbers. And then I compute GCD of the following numbers: bi to the power zi times vi minus 1, whereas I goes through from 1 to k except j. And I add this GCD to the set S as a new candidate modulus. Please notice that this GCD just by construction is divisible by bj to the power d. Each of these guys here is divisible by b to the power bj to the power d. Therefore, it wouldn't be. It always will be non-trivial and will be divisible by bj to the power d. And then I return s, and then I check each element of s if it gives me a suitable modulus for reduction of the equation. And if it doesn't, I can continue constructing more rich and rich sets of modulus. I have no idea, then this procedure stops, and then it stops, but it happens that for many small situations it does stop, and as I shown, there are rather reasonable size modulus exist for many of the equations. So this is the first type of equation I wanted to present today. Now let me switch to the second type of equation, which I call exponential-polynomial Diophantine equations. These are equations of the form certain coefficient k times q to the power n equal to quadratic. In this case, I consider just quadratic polynomial a times m squared plus b times m plus c. K, q, a, b, and c, all the capital letters represent given integers, and the equation needs to be solved in n and m. So there is a noticeable interest to some of these equations. Here just some references mentioning equations of this kind, so they represent certain interest. So how we can solve such equation? Well, the most straightforward way to solve equation is to reduce it to an elliptic curve. To do so, we let a new variable k be q to the power n over 3, rounded down, and alpha b n mod 3. Then equation takes this form, and in fact I consider 3 different equations depending on whether alpha is 0, 1, and 3. Each of these equations represent an elliptic curve, and it is known that there is only a finite number of integer solutions to this equation. So this is kind of immediately proves the finiteness of the solution. However, the problem is this computing solution is that the computations of the integer points on the elliptic curve may be rather lengthy and sometimes even not feasible. And therefore, let us take a look at different approach to the same equation. And what I propose to consider reduction to quadratic rather than cubic equations. In this case, we let k be q to the power n over 2 and alpha be n mod 2. Then we reduce our equation to just 2 equations of this form, quadratic. What is the benefit of such reduction is that such equations is very easy to solve in contrast to elliptic equations. But the problem, however, is that we will be, if it has solutions, it usually has an infinite series of solutions. And therefore, but we know already that our original equation has a finite number of solutions. Therefore, there is a challenge how we can filter out these extraneous solutions for what we get from this reduction. And this is what I'm going to describe today. So, but I need to recall some background. First of all, what is Pell equation? Pell equation is equation of the form x squared minus d times y squared equal to 1. There is a nice general form for its solutions, which can be represented this way. But I'm mostly interested in representing solutions in the recurrent form. So there exists such coefficients a and b that the k plus first solution is a times k solution plus b times k minus first solution. And these coefficients are very easy to compute. Now, next kind of generalization of Pell equation is Pell-Fermat equation, in which case we have not one but general integer n in the right-hand side. This solution has a similar form. There is an extra coefficient standing for first solution, initial solution. But what is important for us is that solutions satisfy the very same recurrent formulas, and even the coefficients are the same. It's just the initial values are different. And then I need to be able to solve Pell-Fermat equation modulo m, and to do so, basically what we do, we take solutions represented in the recurrent form, and then we look for zeros in this sequence modulo m. And there are two types of zeros. The first one, non-periodic zeros that appear. The sequence will be eventually periodic, so maybe non-periodic part in the beginning, but then it becomes periodic. So we may distinguish between non-periodic zeros that come from non-periodic part, and then periodic zeros, which can be represented in the form that xk is 0 modulo m, if and only if k is congruent to some zi modulo r, where r is the length of the period and zi some numbers from the set of integers. Now let us also consider equation, a little bit more general equation than Pell-Fermat equation, in which we have coefficients of x squared, which is not 1. Let's say it's m. This equation can be solved by multiplying the whole equation by m. Then we have a new square here. We denoted x prime, so we reduce it to equation of the form x prime square minus md times y square equal mn. And the original x can be obtained from x prime by dividing by m. So in order to get integer, we need x prime be divisible by m. But this is exactly what we did on the previous slide. We need solutions that gives us 0 modulo m. So basically we can find all the zeros in solutions for this equation. And then in fact each of these zeros can be represented again by a certain second order recurrent formula. So this way we will get solutions to the original integer solution to the original equation. Okay, done with the background. Let us now turn back to the equations that we want to solve. So we have this equation, and outline for the approach can be is explained here. So the first step, we reduce it to Pell-Fermat equation, and I already showed this reduction briefly. Then we let d running through positive integers, d1, 2, 3, and consecutively. And we consider our sequence, which gives solution for the x, modular q to the power d. And compute the periodic zeros in this sequence. And our goal is to eliminate these periodic zeros, because we don't want to have infinite series of solutions. And how we do so, well, I explained how to do so, but if we are able to find such a d, then we can then turn non-periodic zeros into the zeros of the original equation and compute all the solutions to the original equation. So I'm going to explain this in details now. So step 1 is reduction to Pell-Fermat equation. Okay, this is our original equation. We represent it in the form which is suitable for turning into Pell-Fermat equation. And then if n is even, we let x be q to the power n over 2, and we get equation of this form. If n is odd, we let x be n minus 1 over 2 and get equation of this form. Then let us introduce t and s, these two numbers, and eventually we get equation which is Pell-Fermat equation. There's omega is 1 or q depending on the oddness of n. Now, how we our goal now to solve this Pell-Fermat equation. There are two cases. One case then with what was d before is a square. If it is a square, then solution is rather trivial. We simply compute all different factorizations into two factors and solve a system of linear equations. So it's nothing interesting here. There's always a finite number of solutions in this case, and we can get them right away. The only thing that we need to do is to be able to factor this number, ak omega s. So for the rest, let me focus on the case then ak omega is not a square. In this case, this equation represents the Pell-Fermat equation. And solutions can be represented as a recurrent sequence, as I explained before. Here is a particular example which I want to show you, because the theory is rather heavy. It's better to have a numerical example. So let us consider equation 3 to the power n equal 2m squared plus 1. So if n is even, we let x be 3 to the power n over 2, and we have equations of the form x squared minus 2m squared equal to 1. If n is odd, we let x be 3 to the power n over 2, and we get equation 3x squared minus 2m squared equal to 1. So in combined form, they can be written as cx squared minus 2c m squared equal to c, where c is 1 is if n is even, or c is equal to 3 is if n is odd. And it can be easily checked that 2c in this case is square free, therefore it's a representative Pell-Fermat equation. Now, let us solve this equation. So for c equal 1, solution is given by the following recurrent sequence. X0 is 1, x1, x3, and xk plus 1 is 6, xk minus xk minus 1. And for c equal 3, solution is x0 is 1, x1 is 9, xk plus 1, 10, xk minus 1. Here is the numerical values of this axis. So 1, 3, 17, 99 in one case, and 1, 9, 89, and so on in the other. Our goal is to find all powers of 3. Remember x, then we did reduction, x was a power of 3. So our goal to find all powers of 3 in these two sequences. So here we go to the step 2. Let us consider our equation modular q to the power of d, whereas d will go from 1, 2, and so on, until we reach suitable value of d. And I will explain what is suitable value of d. So our goal is to find such a value of d that all periodic zeros modulo d have some other prime factor which doesn't divide q. If we have other prime factor which doesn't divide q, it immediately implies that these numbers can be powers of q. So this is a kind of underlying idea, and here's an implementation of this idea. So let d goes from 1 to 3, and so on. So this procedure may in some cases may not stop. So we have to interrupt it manually and then just admit that they cannot solve the particular equation. But if it stops, it kind of provides a certificate and gives all the solution. So what we do for each d? We compute set of indices of periodic zeros in the sequence xk modulo q to the power d and the period r. Then we go through all these periodic zeros. So S is a current periodic zero, and that's not zero itself, but the index of the zero. And we take the xs, x sub s would be periodic zero in the sequence, and xs plus r would be the next periodic zero corresponding to, since r is a period, it would be another periodic zero from the next period. So we compute the GCD of these two guys, and just by construction you can immediately notice that this GCD must be divisible by q to the power d, simply because r was a period, and both these guys are divisible by q to the power d. But we are not interested in q to the power d. We are interested if we catch something else in there. So we basically remove all primes that divide q from this number, and then we check if we have any primes in y left. So if there is such a prime, we compute a period q of xk modulo p. And if it turns out that q divides r, it means that every time we have 0 modulo q to the power d, we have 0 modulo p. But if it is 0 modulo p, it can be power of q. So we eliminate 0. So this 0 doesn't give solution to our original equation, and we can eliminate it. And so after running these loops, if it happens that we eliminated all zeros, we are lucky. We can now get all the solutions to our equation. And let me go back to the numerical example so it will be more clear. First of all, let us consider case c equal 1. Let d be 1. In this case, the set of indices of periodic zeros would be k, which is 1 or 3 modulo 4. So the first 0, x1, is 3 to the power 1. We see that there is no other primes besides q. So q is 3 in this case. There is no other primes besides q, so we cannot do anything. We need to go to the larger value of d. Therefore, we go to d equal 2. If d is equal to 2, then a set the indices of the periodic zeros in my sequence is 3 and 9, or 9 modulo 12. Let us consider the first guy, x3. x3 is 11 times 3 to the power square. We see that here 3 to the power square, which is expected. It is a q to the power d, but we have also 11 here, which is a nice thing. So let us check if what is the period and what are zeros of xk modulo 11. And we obtain just by chance that zeros modulo 11 are exactly same 3 and 9 modulo 12. What it means? It means every time we have divisibility by 9, we have also divisibility by 11. It means that periodic zeros do not deliver solutions to the original equation because we want powers of 3. But there is always factor 11. Right? And here you can see an example. So here's d equal 1, we have xk modulo 3 is a periodic sequence with period 4, and there are exactly two zeros here. If d is equal to 2, we have sequence xk modulo 9, and the period is 12, colored green here, and we have two zeros, 3 and 9. However, if you consider the same sequence modulo 11, we have the very same period of length 12, and the very same zeros at 3 and 9. Therefore, we eliminated this 0. Now, case equal 3. Again, for d1 and d2 in this case, we cannot do much. However, if you take d equal 3, the set of zeros is k4 or 13 modulo 18. And if you consider the first zero, which is x4, x3 to the power 3, which is expected, this is q to the power d. And then we have 17 and 19. And it turns out that if we compute xk modulo prime 17, we obtain the very same 4 and 13 modulo 18. Here's an illustration. This is the period modulo 27, and here's the period modulo 17, and we have the very same zeros. So every time we have divisibility by 27, we have this divisibility by 17 as well. So we eliminate. Now we come to, in both cases, we were able to identify suitable value of d. So we come to the case that we need to the step that we need to compute solutions to solutions m and n to the original equation. Now let us recall that x was q to the power n over 2 or q to the power n minus 1 over 2. The obtained value of d implies that the exponent of q and x should not exceed d minus 1. Remember, if qd divide x, there is immediately divisibility by some other prime. Therefore, the power of q must be bounded by d minus 1. It cannot be d or larger. So we have immediately that n is at most 2d minus 1. And if n is at most 2d minus 1, we simply can go through values of m and check if there is a suitable value of m. And this way we will get all the solutions. Here are all the solutions for the equations which we considered as an example. I'd like to thank Jijian Wang. She's my student, and National Science Foundation for supporting this issue. Thank you.